So our next talk will be given by César Alberto Díaz Hernández of the Faculty of Sciences at UNAM, National University of Mexico. And he will talk about complexity of magnetization and magnetic simplification. Please go ahead.
Yes, thank you for the introduction. And first of all, thank you to the organizers for inviting me to giving this talk. This talk will be based in this article that we published earlier this year, yeah, along with Daniel Avila and Leonardo Patiño. You can see the number here. So, okay. First of all, I'm gonna talk to you about what is computational complexity in case you're not familiar with the concept. How we can compute it, what are the possible ways to set a dual quantity in the holography for the complexity. And then I'm going to talk about how we can compute this complexity in the case of a magnetic brane, in the case of a quantum state immersed in a magnetic field, and what consequence adding a magnetic field can have to the complexity. Okay, so what is computational complexity? In case you're not familiar with this, you can think of complexity as a measure of how difficult it is to accomplish a certain computation. This concept arises in the context of computational science and quantum computing, but it can be generalized to any physical system. So for example, imagine you have some quantum state psi, and you want to obtain that quantum state by applying certain unitary operators to some reference state. I don't know, you can think of this like you have a certain laboratory, you have a quantum state, and you cannot apply any transformation you want to these states because, I don't know, the equipment in your lab doesn't allow to perform any operator, so you have a limited amount of operations you can perform. So these operators is what we call the quantum gates, is the operators that you have available. And you can perform these operators to any quantum states and transform it to another quantum state, right? The minimal amount required to make this transformation, or to perform these transformations, is what we call the complexity. Intuitively, as I told you before, you can think of this as how difficult it will be for you to accomplish this new state, right? If you need to apply more operators, it will be more difficult for you, right? So this intuition, the intuition we gained for this is that this complexity tell us how difficult it is to reach this quantum state, right? Initially, you could think about a computer. Imagine you have some computer or a quantum computer, and you have to make some computation, right? How hard will it be for you to make this computation? Well, you can think of it as how many processes, how many operations your processor needs to do, right? So you can think of complexity like that in terms of computers, or in terms of quantum computers, or in terms of how much energy it takes to take one physical system from one state to another, or how much time it takes for a system to evolve to a certain new system, new state. All these ideas give us an intuition of how hard it is to make these operators, these operations, but of course, all of these ideas are equally valid to define a complexity. So the definition of complexity is not unique. You could also think about the example from before about you're in your laboratory, you have a certain amount of operations or transformations you can apply to your quantum state, but you can go to another laboratory and they maybe have another equipment and they have another set of quantum gates, right? Another set of quantum operations that they can perform to their systems. And the exact number they will acquire when computing how many operations they need to perform will be different because they have different operators, right? So this definition of complexity is not unique. There is some ambiguity there, but we can talk about how separated these operations are, right? How separated these states are in the sense of how difficult it is to change one state from another. Okay. Then in the context of holographic duality or the ADS-CFT correspondence, as we all know, according to this duality, asymptotically anti-de gravitational background in 10 dimensions is dual to a field theory in less dimensions, right? Usually these correspondence take the form of ADS5 to CFT4. This means you can compute some certain things in an anti-de Sitter background in 5 dimensions, and this will give us information about a certain quantum field theory in 4 dimensions. This is usually the way one found the duality in the literature, but in general, this should be an ADS5 times an S5 manifold, right? Times a compact manifold in 5 dimensions, and this is truly dual to the CFT4. We usually don't encounter this extra manifold, this extra 5-dimensional manifold, because we use systems in which the equations of motion in the ADS5 setup, if we can satisfy the equation of motion in this ADS5 setup, then the equation of motion in the full 10-dimensional setup can be satisfied, right? If we can find a system like this, we say that we have found a consistent truncation of the full theory, and we can only work in the ADS5, right? And the duality and the correspondence will stay valid. What we usually do is to find a solution in these ADS5 dimensions, in this anti-de Sitter in 5 dimensions, work with our solution there, and then maybe we can find an uplifting solution, right? We can find a way to uplift that solution to find fields in the 10 dimensionals in terms of the fields in the 5 dimensions in order to satisfy the 10-dimensional equations. So we usually don't bother about the extra 5 dimensions, right? In the context of complexity, these extra dimensions may be relevant. So keep this in mind. Okay, and this duality gives us a dictionary to relate the quantities on both sides of the duality. And if we have a dictionary, we can ask ourselves, what is the holographic dual to the complexity? Or what quantity in the side of gravity, in the side of the anti-de Sitter background, will be a measure of how difficult it is to evolve a certain state or to transform a certain state. There are two main proposals for this. The first proposal is the complexity equals volume, and the second is the complexity equals action. I'm not going to talk too much about the second one, the complexity equal actions. I will be focusing on the first one, the complexity equal volume. But just know that this is not the only one, right? Okay, it turns out that the complexity has similar properties to the volume of an eternal black hole. If you see this Penrose diagram, in blue, there is the interior of the black hole, and in gray is the exterior of the black hole, right? Where this R coordinate is the radial coordinate of anti-de Sitter, where the boundary is found at in R equals infinity. And we have some singularity, some radius where we found the singularity of the black hole, and some radius where we found the black hole horizon. Okay, how can we compute the volume of this eternal black hole at a certain time? What we can do is to take a slice, a time-like slice, sorry, a space-like slice, anchored at a certain time at the boundary, and unite our two sides of the black hole, right, with this space-like slice. Notice that if the time evolves, if we move in time, the volume of this space-like slice will increase as we move in time, right? In the interior of the black hole, we have just this little volume here, but if we move in time, the volume will increase, right? So we can relate the volume of this black hole with the volume of a maximal space-like slice, sorry, anchored at a certain time. Okay, so the complexity equal volumes relates this complexity of the boundary of states with the volume of a maximal space-like slice ending at a boundary at a time that we call tau. There is some constants here, some proportionality constants, where Gn is the Newton constant. And this L is a length scale. As I told you before, the complexity is not uniquely defined. So this scale gives us this liberty, this ambiguity of how we can define our complexity, right? Usually this is taken as the radius of anti-de Sitter, and we can set it to 1 without a loss of generality. So the actual number we can obtain from this relationship will differ depending on which length scale we choose. However, even if the complexity is not uniquely defined and everyone can have a different number for their complexity, we can compare these complexities of different states. If we take the zero temperature vacuum state, we can compare it with the complexity of a finite temperature non-vacuum state at times tau equals 0, right? So this is what we call the complexity of formation. This intuitively can tell us how difficult it is to form a certain state. Imagine you have the vacuum, you don't have anything in your theory, you don't even have temperature, and you ask yourselves, well, how difficult will it be to construct or to form a different state, a state with some matter, with a finite temperature, with some fields in it. You can compute the complexity of these two states and obtain what we call the complexity of formation. How hard will it be to form this new background or this new theory from the vacuum state? The complexity of formation is given by tau equals 0, but the time in the boundary set to 0. I mean, we would need to compute the volume of this space-like slice, the blue one. But we can generalize the concept to any time we want. To this quantity, we call it the evolving complexity. It's just a complexity of formation, but for a general time, every time, anytime we want. Okay. Then what we did in the paper is to consider some gravitational background. We wanted to add a magnetic field and to see what happens to the complexity of formation or the evolving complexity when we add this magnetic field in the theory. Okay, so we can start from a general 10-dimensional metric given by this line element in 10 dimensions, where this we have here a line element in 5 dimensions. This usually will be a line element relating to the anti-de Sitter 5. And here we have the extra dimensions of the compact manifold in 5 dimensions. That is usually a sphere. So we will have 5 directions here: the theta direction, the psi direction, and other 3 angles, which are the 5 directions. Okay, and we can set certain fields in this general setup. The equation of motions will follow from this action where we introduce these new fields, these scalar fields, bar phi, and some gauge fields A, where these F's are the exterior derivatives or gauge or for gauge fields. We will have 3 of them, gauge 1, gauge 2, gauge 3, and we will have 2 scalar fields, right? Scalar 1 and scalar 2. And even if these line elements in 10 dimensions or this action can be a bit overwhelming, but we can simplify it by setting some of our gauge fields and our scalar fields to certain values. For example, the vacuum states can be accomplished by setting all our fields to 0. In that case, our 10-dimensional line element, I think there is a raised hand. Luis? Yes?
Yes. Cesar, what is capital X in your action?
Yes, this capital X is the same capital X that appears here in the line element.
But it's a function, it's a number, it's
yeah, it's a
okay. I see on the bottom of the slide.
Yeah, you can think it as a function relating to the scalar fields and these directions in the 5 sphere.
Okay, thank you.
Okay. So as I was telling you, we can accomplish the vacuum state by setting all our fields to 0. In that case, the line element gets very simplified, and we recover an anti-de Sitter metric in 5 dimensions. So we wanted to test different backgrounds involving a magnetic field. The first one is one of the most basic backgrounds that include one, being the Docker and Krauss background. This is obtained by setting our scalar fields to 0 and setting all of our gauge fields to this quantity relating to only one gauge field. If we do this, our line elements simplified like this. And the second one is the Avila and Patiño background. Background was developed by Daniel Avila and Leonardo Patiño. That can be obtained by setting the 2 scalar fields like this, relating to just one scalar field, the gauge 2 and gauge 3 field, all being equal to or proportional to the gauge field to just one gauge field, and the third one, the gauge field A, the gauge field 1 set to 0. Okay, when we put these fields in our 10-dimensional setup, or line elements simplified like this. And everything that appeared there, all our x and our delta, take this form. This is a little more complicated line element that we had in the previous background. But one important thing to notice is that this delta factor appears in the 5-dimensional line element. This will be relevant for the computation of the complexity in 10 dimensions, so keep this in mind. But in both cases, the 5-dimensional line element and the gauge strength tensor takes the following form, where we have a magnetic field pointing in the Z direction, and the metric functions relating to the 5-dimensional line elements can be computed using a numerical analysis. So we will only care about computing these metric fields or these metric functions. So, as I was telling you, both theories represent a finite temperature field theory immersed in a constant magnetic field of strength B in the Z direction. The main difference in these two backgrounds is, well, the appearance of a scalar field in the AP model. This scalar field will be dual to a non-vanishing vacuum expectation value of a single trace operator. And this BEE will be depending of both the temperature and the magnetic field strength of the theory. This AP model has been used to add fundamental degrees of freedom in holographic theory, meaning it can be used to model mesons in a quark-gluon plasma. And so it is relevant to study this kind of backgrounds, not just for the quark-gluon plasma, but for modeling mesons in general. One particularity of this model, of the AP model, is that there exists a critical magnetic field for which the theory becomes unstable. These start to develop a naked singularity. So below this magnetic field, where the solution is still stable, we can find two branches of our solution. One that is thermodynamically preferred, and this is what we call the stable branch. The other one being the unstable branch. So we will have two different solutions. And well, knowing all this, we can now compute the complexity of these two theories. First, we computed the evolving complexity in the 5-dimensional setup of the Docker and Krauss model, the model that only adds a magnetic field, and we can find an increasing behavior of the complexity. The red one, you can think it of the complexity as the complexity of formation, the complexity where tau equals 0, and the blue one, you can think it as an evolving complexity. This is an expected behavior, right? One should expect that forming a state with a strong magnetic field should be more difficult than forming a state with a low magnetic field or with 0 magnetic field, right? So as the magnetic field increases, the complexity also increases. However, for the AP model, the complexity has a more interesting behavior. As you can see here, the complexity for low magnetic fields is increasing, as we should expect, but we can find a certain value of the magnetic field around here, where the complexity starts decreasing. Here we show the stable branch in the solid line and the unstable branch with the dashed line. So even for the stable branch, we have decreasing complexity with the magnetic field, right? We can ask ourselves, well, why this is happening? Why the complexity is decreasing? I would have imagined that the complexity will always increase. Adding magnetic fields should make more difficult for me to form the states. So why is this happening? We can introduce the complexity of magnetization as a quantity that tells us how the complexity change as the result of just adding a magnetic field. Notice here that we're adding a lot of things. We're adding not just the magnetic field, we're adding a temperature, we're evolving it in time. So all these contributions could be the cause of this decrease.
So, 4
yes?
minutes more.
Yes. So to isolate this behavior, we introduce the complexity of magnetization. For the decay model, again, we obtain the expected result for this complexity of magnetization. Again, this tells us that if we add a magnetic field, it's more difficult to form these states. But for the AP model, we notice that this decrease of complexity also occurs. This tells us that this decrease in complexity is a result of adding this magnetic field. Okay, so there are some solutions, as we can see here, that have a complexity of magnetization less than 0. So for a certain magnetic field, the complexity starts decreasing. We can say that the state is less complex, or that it simplifies. The state gets simplified. This is what we call the magnetic simplification, a simplification of the system due to the works of the magnetic field. Just to finishing, I don't have too much time. This phenomenon occurs for every time we found. Once the complexity starts decreasing, if we evolve in time, the complexity will not increase again. It will continue to decrease. We can do the same thing in 10 dimensions. And if we do the computation in the full 10-dimensional background, we see that in the case of the decay model, the results are the same. But in the case of the AP model, depending on how we do the computations, if we flip the solution we had in 5 dimensions, or if we find a new space-like slice and maximize that in the full 10-dimensional theory, we have different results. At least in the uplifting solution, we have a similar behavior. So this simplification, this magnetic simplification, seems like it's not just only a product of the consistent truncation we're using, but it seems that it's a phenomenon that occurs in general for the 10-dimensional setup, and in general for this type of background where a scalar field is involved. So in conclusion, we encounter this phenomenon of magnetic simplification, where the states become easier to form than the vacuum states for certain magnetic fields. You could think this maybe a rough sketch in a computer. If you have some problem that your computer is not able to solve, you could put it in some magnetic field with some scalar field playing with it, and you could simplify your problem, right? You could make your computer able to compute this very hard problem that you encountered before. This does not happen with the Docker and Cross model, the model with only the magnetic field. So the interplay between this gauge field, this magnetic field, and the scalar field seems to be responsible for this simplification. It's not only the magnetic field, but you need also these scalar fields. And well, it has been noted in the literature earlier that adding this type of scalar fields can dramatically alter the behavior of the complexity of formation. Not only here, but there have been other examples where the complexity of formation becomes negative for backgrounds with some sort of a scalar field involved. However, it is not clear if this is a general statement or is a result of the consistent truncations. As I told you, the complexity is not uniquely defined. We could find another reason to change the dual complexity or to change how we compute it in the full 10-dimensional background. So there is still some things to investigate here. There is still some work to do here, but everything seems to imply that.
Time is over.
Sorry?
Time is over.
Yeah. This is just all. This would be all. Thank you.
Okay, let's thank Cesar. And if there is some quick question,